Hello. As a prelude to my talk today, I'd like to ask you to perform a simple task. It has three parts. In the first part, I'd like to ask you to pick a number between 1 and 10 and count upward by threes. We'll do that for 5 seconds. Then we'll have a 5-second pause, and then we'll do that task again, choosing a different number and counting up from that number by threes for another 5 seconds. Okay? Begin now, choosing a number between 1 and 10 and counting up by threes. Now, pause or rest for 5 seconds. And now choose a different number and count up from threes from that. Okay, thanks. A large part of cognitive neuroscience has been concerned with what you were doing during the task, the counting upward task, and thousands of others like it. But in the last decade, attention has focused more on what's going on in between the tasks, in that pause, in the rest between the two tasks that lasted for 5 seconds. That of activity has come to be called the default mode. There seems to be a network of brain areas that are reliably activated when the brain is on pause or between task blocks in any experiment. And this has become of great interest in the cognitive neuroscience community. Different functions have been proposed for the default mode, and a lot of these have been linked to a conception of consciousness. The Jamesian stream of consciousness. This, I think, is an interpretive mistake. James did not intend his stream of consciousness to refer exclusively to what happens when the mind or brain is disengaged from the world around it. Rather, he intended it as a characterization of the flow of thought in all situations. Most of James' examples in the principles of psychology are in fact drawn from perception and action. Stream of consciousness that seems to be in play these days, then, is a different meaning of that phrase, one originally coined by May Sinclair in 1918 to characterize a literary device in which authors recorded the internal soliloquy or monologues of characters. James Joyce's Ulysses is perhaps the pinnacle of the form. It's this literary stream aspects of the default mode certainly seem to be affiliated with the activities of Molly Bloom and the other great soliloquizers of the literary tradition. And here, of course, there is a great deal of relationship to different forms and states of consciousness. Among them, though, I'd like today to just look at one thing that may have been going on with you while you waited for those 5 seconds for something to happen at the beginning. Namely, the passage of time. One constant content of the default mode is an awareness of the passage of time, a sense that you're near the beginning or the end of the pause which I announced to you at the beginning of the experiment. Understanding temporality, this awareness, will then be a main goal of any theory of consciousness. It is, of course, a difficult one. It's difficult for many different reasons, but one of them in particular has to do with the assumptions which are built in at the foundation of functional neuroimaging. The underlying question here being whether neuroimaging can be revealing to us of the consciousness of passing time. Is one that I will call task clamping. It's the idea that brains do what we tell them to do, when we tell them to do it, and they're doing nothing else for that period of time. And so in a hypothetical task where there are 3 conditions or 3 stimuli, A, B, and C, the idea is that the brain is entirely devoted to the processing of A, and then when B begins, entirely devoted to that, to the exclusion of all else until something else happens. And that enables an exploration of state A by contrasting it with state B in the contrasted method which is prominent in so much cognitive. But this is not how the mind works, and I believe the prelude task in this talk illustrates that. During that state B, if that's the pause or rest state, there isn't simply a kind of being consciousness. Rather, there is an awareness of the position of each moment of the otherwise unmarked passing stream, an awareness of the context in time of that moment. And so at the beginning of the rest, one's aware that the rest has just begun. After a few seconds elapse, there is an expectation emergent of the coming to the end of the rest, and so forth. This is the fundamental insight of Edmund Husserl in his lectures on the phenomenology of internal time consciousness, originally given in 1905, but revised and then published in 1928. Husserl described that context, the retentional consciousness of what has just passed, and a protensional or anticipatory awareness of what is about to come, as flanking the primal impression, the immediately given present situation, and this being a constant feature of every moment of conscious experience. One immediate consequence of this is that one's state of mind is continually changing as time passes, and that block the inference in cognitive neuroscience that allows us to block together moments in the passing stream and subtract one from the other to find out what's happening. And it's quite easy to demonstrate in functional neuroimaging that there is continual change in the images. This continual change is omitted in most functional neuroimaging studies just because the images are blocked together and subtracted. How then does the brain support the awareness of passing time? In the remainder of this talk, I will look at a particular fMRI case study to ask a couple of questions. Can we determine, first of all, that these brain image series do in fact encode temporal information? And if so, can we determine which areas of the brain seem to be particularly involved? Can we speculate about how the brain might do this? And finally, in the background, how might we be thinking about fMRI as a research tool for other kinds of questions, outside of the standard questions in standard approach? Since we are talking about internal time consciousness, it is good, I think, to look at the default mode as our area of interest, or our times of interest, mainly because other tasks are off the table at that point. It is during that pause in my initial task that you were aware most prominently of the passing of time. It's a promising place to be. But we can't use standard in which we block together moments in the stream of consciousness and separate those from other blocks of time, because, as discussed, there's change. And so what we need is a different initial method of reducing the enormous complexity of fMRI data, separate signals from tens of thousands of pixels or voxels. Instead, we need to look at a way in which we can simplify the activity of the brain without necessarily presupposing that we know when things are happening and when they're not. One method of doing this is called independent component Independent component analysis is a way of determining ensembles of voxels or regions of the brain which are active and inactive together. In this example, a subject is looking at a flashing stimulus in the right visual field. It's on and off 4 different times during the course of the experiment, and these voxels are active together. They're either on together or suppressed or off together, and the time course on the right side of the slide reveals that activity as time. Independent components, and I'll refer to them just as components for the rest of this talk, can be spatially isolated or very distributed. They can be artifacts, as in the top right slide here, and they have different time courses, different periods of activity and inactivity as time passes. A technique like independent component analysis then enables us to operate outside of the assumption of task clamping. With this, we can look at each particular time point in an experiment and look at the pattern of activity over the many components which have been isolated by independent component analysis. And that's what we're going to do. We're going to do this with the help of an fMRI study originally conducted by Grady and colleagues. It's archived in the fMRI data center, and so that data is available for reanalysis, which we have done here. Grady looked at young, middle-aged, and old subjects. For this analysis, we extracted a subset of old and young subjects. The structure of the experiment is essentially this in the sessions that we analyzed. There's a task, 2 tasks in fact. Those are not of interest to us. What we are interested in is in the alternating default mode segments, the moments of pause, each of which lasted 24 seconds between all the tasks. Our first strategy then is to see if we can identify the components that were first extracted by ICA that are most correlated with the default. And this we can do to discover that this is an overall pattern of activity which is most active in default mode. This is a glass brain view. We're in a sense looking straight through the brain in these 3 different axes, with the redder end of the spectrum being areas that are active together during default mode, and the bluer end, those that are suppressed, together during the default mode. This then can be compared to the canonical default mode, summarized from several different studies with a fairly good match. In other words, what we're seeing in the Grady study is the default mode reasonably close to other Having identified those components, then, we can ask a more specific question. Namely, what's actually going on during that pass in the default mode. These default mode periods, or pauses in this experiment, last 24 seconds each and alternate with 24 seconds of various tasks, which we're not interested in. If we look even more closely at the structure of the experiment, we can think of it in the following way. During the tasks, T1 and T2, we're not at all interested in what's going on, and so we will essentially regard them all as zero, as off the table. But during the default mode, we are interested in the exact sequence of time steps. The idea being that the first, or the beginning of the default mode, has a different temporal feel, or temporal awareness, towards the middle, compared to the middle and the end of the default mode blocks. Can we recover this kind of information? Can we determine patterns of activity which are specific to specific moments in time that in turn are promising candidates for the temporal correlates, the neural correlates of temporality? We're going to do this using a brain reading technique. That is a machine learning technique which will enable us to decipher complex and distributed patterns of activity that would not otherwise be visible to us. And we'll use that technique to attempt to recover the serial position 1 through 24 during each of the 24-second default mode blocks. Again, to look at the fine structure of this, we're going to see if we can learn to read the brain to read off 1 through 24, that is the serial position, or the elapsed time. The default mode passages. This will require a representation of the target data, that is, how to represent the time steps that we're going to attempt to read off of this distributed data. We'll do this using a binary encoding scheme that's really quite simple, in spite of the busyness of this slide. For each of the time points from 1 to 24, we'll use a matching number of ones, of binary bits. In effect, time point 2 is encoded with the number 2 ones and the rest minus ones. We can color code this as follows, and in a minute you'll see why the color coding is appropriate. Here. So we see that there are the 2 ones to encode the number 2, and then the 22 blues, or minus ones, to encode, as it were 22 time steps from the end of the default. And this same strategy will be used to encode each of the other time steps in each of code blocks. And so the entire structure of the experiment can be color-coded and will look something like this. The zeros are the light greens, which are the off-the-table task periods that we're not interested in. But the default mode reveals an evolving pattern of temporal positions, and those are encoded in the vertical array of blue and red bits. To zoom in on that one last time, we see how that color coding represents, in fact, a pattern of binary bits. Our machine learning technique is called support vector machines. As in other machine learning techniques, what's going on here is a distinction between a training stage where the technique, the support vector machine algorithm, discovers a method of separating training stimuli into 2 groups according to our a priori sense of where they should be divided. Phase in which a new or test stimulus is itself assigned to one group or another, and we assess whether the performance has been correct. We always have in the back of our mind target, and that target is that temporal structure that we've now encoded. We use the first half of each experimental run to train the support vector machine, and the second half to test. The idea is that if after training the support vector machine can look at brain patterns, independent component patterns that it has not seen before, and correctly tag them with their temporal position in the experiment overall, that will provide presumptive evidence that there is information in the underlying images which specifies temporality. In other words, there's something for the support vector machines to look at that is determinative of the position in time. The success of the support vector decoding enables us to say that there must have been So now we turn from the target, our expectation of what we want the temporal sequence to look like, to what the support vector machine is actually able to recover from the images alone. Can the support vector machine learn to segregate images? Yes, it can. And this is the color coding now of the actual output of our support vector learning algorithm. And we can see that it matches the pattern of the target outputs, that is to say, the temporal pattern of the experiment overall, successfully recognizing the difference between the task and the pause of default mode conditions, and more importantly, establishing the temporal position approximately of each image of the 24. The default mode sequence. There are slightly different success rates for the old subjects in the middle band here and the young subjects in the bottom band. But the overall finding is that it is possible to make sort. We can condense the information given in the color coding into a graphic summary of the success of these networks in recovering temporal information. And so now superimposing all four of the test blocks in the default mode conditions, we can see that early on serial positions are not reliably recovered, but then towards the middle, say 5 seconds, and on towards approximately the end, in at least 3 of the 4 default mode blocks, there's a fairly good success across all the subjects and all the runs with the support vector machine recovery of temporal information. So what we have so far then is evidence that in fact temporal information is indeed encoded in fMRI image series. But the next question arises, which components are significantly active at each default mode time point? That is to say, is it the entire brain, or are these images across the board that support the temporal information encoding? Or can we isolate subsections of the brain that themselves are encoding the temporal information? Are there particular components associated with each time point or each elapsed duration? The default mode. We'll approach this through another strategy, which we'll call the leave one out strategy. You may recall in 2001: A Space Odyssey, Dave has to disable Hal by turning off his higher cortical functions one by one. Hal's performance degrades accordingly. This is essentially the leave one out strategy in a nutshell. We will go through the components now that were originally established through independent component analysis, and we'll disable them one by one and go through the entire SVM test procedure, training and test procedure again. Then we re-enable that component and disable the next. For each one of these, we perform the same measurements that we did initially, and record and note then which components have the greatest effect on the overall performance of the network. Those components, the ones with the greatest impact, then become the most important components in explaining the overall success of the machine learning algorithm. We repeat these steps, and as we go, we're slowly reducing the number of components available. The performance overall degrades, and in that way we can establish which of the many different components of the brain are most responsible for the ability to encode temporal information. These then are glass brain images. Once again, we're looking through the brain along three axes of the independent components that are most involved in encoding temporal information. These are the parts of the brain which, if removed, most degrade the ability to encode the passing of time. Dark areas are indicating positive activity, and the light areas decreased activity. It's an evolving landscape as time passes through the 24 seconds of the default mode blocks. But if we look at the areas where there is the greatest amount of change, bring together a single network or a single set of regions which seem to be most involved in the encoding of elapsed temporality. And that's A, or the top panel of this slide. Those are the voxels that are most associated with the ability to recover temporal information in this experiment, in this reanalysis of the Grady data. Below in B, then, are the voxels which are most significantly associated with the default mode. So we have our basic default mode in the bottom panel, and then our dynamic temporal network, the areas of the brain which are most involved in encoding temporal information, in our top panel. And the takeaway empirical lesson of this talk then is in the comparison of these two panels. The revelation being that there is a significant overlap then between the top, the dynamic temporal network, and the bottom, the default mode network. And that suggests as a conclusion, at least based on these data, on these subjects and runs, the conclusion that one function of the default mode network is the encoding of temporal information. At this point, though, we can entertain a few quick objections to the inferences that have gotten us to this point. One objection is, why should we regard this temporal information as any component of consciousness? That's just another restatement of an objection which could be made to fMRI data across the board. If we had a picture of what parts of the brain were responsible for, say, the counting task at the beginning of this talk, we'd raise that same objection. Why should these voxels be at all associated with the state of consciousness? And I think we have to consider this en masse in all cases. If we regard fMRI data as revealing anything about dynamic activity in the brain underlying consciousness, the inferences for any task will be either licensed or not, and that's the same in this case as well. Another objection, though, might be that the temporal processes, things that evolve in time, are not simply limited to the awareness of the passage of time, but encompass other kinds of dynamic or slow changes that might not be conscious or might not be characterized as temporal consciousness. Examples of these might include fatigue, waning awareness or attentiveness, and so forth. The general reply to this objection is probably best made based on this slide, which we saw a few minutes ago. If there is a consistent fatigue effect or any other effect, it is one that does follow a fairly close time course to the time course of the experiment itself. What we notice in this slide is that there's a great deal of consistency in the recovery of temporal information from each of the default mode positions in each default mode block. And so if it is another effect besides the awareness of passing time, it's one that maps pretty reliably on the ticking seconds of each default mode block. In fact, we do see some evidence of fatigue here, and that's in the fourth default mode block, in which the success rate is quite a bit lower than in the other three. And that may indeed be flagging attention or some other effect. But within each block considered by itself, there is a striking consistency and a fairly particular determinant ability to recover temporal information. If it's not the awareness of passing time, then it is something that behaves very much like the awareness of passing time. And the distinctions and arguments that we might have from this point is what the exact phenomenology of passing time is like, how that is encoded in phenomenology as well as in the brain. But that is not to deny, then, that it is temporal information which is indeed recovered by this analysis. And other objections I hope we can discuss afterwards. I want to close, though, by at a little bit about the dynamics and the way the default mode components might contribute to the awareness of time, not just during the default mode, but overall. And here the observation, which is quite striking, I think, is that even the components which are most strongly associated with default mode are only slightly more active during default mode than they are during the rest of the experiment. For example, the component on the lower right, which is significantly correlated with default mode, is only active above its mean, that's the red line, 52% of the time during the experiment. It happens that activity is ever so slightly more tilted towards default mode, and that's enough given the number of data points to make it a significant correlation. If we consider all the default mode components in our old subjects, on average, they're really only about 57% greater than the mean. That means, in a sense, that they are active almost half of the time during non-default mode, during the task components. And that's not too different then for the young subjects in the Grady study as well. The take-home message here is that whatever it is that supports time is active throughout the experience of this experiment. In a way, it's less conspicuous while other tasks are going on at the same time. Way along. And it's in a continual dynamic change. In other words, it is a distributed and rapidly changing pattern of activity that supports the representation of passing time. So if we look in one subject here at 5 default mode components, the time course of the experiment being the black lines, we see in the colored lines a great deal of oscillation. We can superimpose the default mode components and average them, and we see this more vividly. They are not only oscillating around their mean, but doing so on a very different time scale. Each has its moment of peak activity, which in a sense is the moment that that peak activity is available to encode the temporal position in the unfolding sequence of the This slide makes this both iconic and, I hope, sonic. On the panels of graphs here, we have the aggregate of all of the significant default mode components in our two groups of subject, old on the left and young on the right, indicating that overall there is dynamic change, both continuous change but also punctate change, and so a great deal of dynamic representation of time. We can turn this into sound in the following way by assigning each of the components a tone and making that tone louder or softer according to the intensity or the magnitude of the component. And so in one subject, subject 39 as it happens, we take just the default mode components and we can hear in an oscillation between a low and high tonal structure the ebb and flow of task and default mode. This is also audible in a young subject. but even audible if we listen to all of the components together. Go back to our old subject then, and now not just the default mode, but all of the components together, and one can hear still the oscillation between task and default mode. In conclusion, in this talk we've discussed ways in which temporality is both phenomenologically essential and psychologically demonstrable. These are the starting points and the assumptions. But also we've explored evidence that the temporal evolution of awareness is detectable using fMRI. And furthermore, that the networks that particularly support temporal encoding of information are networks which overlap with default mode cognition. Thank you very much.